Good morning, everyone. My name is Heather Dells with Graybar, and I would like to welcome you to Graybar's G2 Talk presentation on how best practices for gigabit service delivered over hybrid architecture. We have a great discussion lined up for you today, but before we get started, I would like to cover a few housekeeping items. First of all, if you were one of the first 50 people who joined in on this presentation, you will receive a coupon for a free cup of coffee, courtesy of Graybar, as a thank you for your time today. At the bottom of your screen, you'll see a box for Q&A. Feel free to submit questions throughout the presentation. We'll address as many questions as time permits at the end of the presentation. Lastly, our G2 Talks are all archived on the graybar.com website, so you'll be able to view this presentation again or recommend it to others. We're happy to team up today with Viavi. As a distributor, Graybar works alongside Viavi to help network service providers prepare for the future. You can visit graybar.com to learn more about our solutions. At this time, I am happy to introduce today's speakers, Stephanie Burris and Thad Ward. Stephanie Burris is a Solutions Marketing Manager for Viavi. She markets Viavi solutions that address new test cases for customers and works to help educate customers globally. Thad is the North American Product Line Manager for Viavi. He is responsible for home and field test instruments covering all broadband services. He is currently working with several customers on developing new test procedures for fiber to the home and G.fast. So without further delay, I would like to turn the presentation over to the Viavi team. Take it away, Stephanie.
Welcome, everyone. Thanks for joining us today. We are going to be talking today about best practices for test of residential gigabit broadband. There's a lot going on in this space. As you think about it, we've got DOCSIS 3.1 coming out, new fiber to the home, and new DSL profiles as well, like G.fast. So we're going to talk about fiber and the G.fast XDSL profiles today, as well as some of the things that can go on in your wired and Wi-Fi home networks. All right, so today this is our agenda, and we're going to talk about, what are we trying to do for our customers, for our end customers. And this picture here represents a family that we want to see, having digital harmony in the home. They've got a lot of applications that they're interacting with, and we want to make sure all those work for them and that they've got a good experience and they're not aggravated, right? So we'll talk about that. We're going to talk about some of the newer technologies that are coming out, like fiber to the home and G.fast. We will talk about best practices for each of those for the fiber to the home and DSL test. And then we're going to swing on into the home and look at what can go wrong with the home network and the wiring in the home network, as well as the Wi-Fi network. And then we're going to talk about speed testing. So when you think about this picture here of this little home, you think about how complex the home network is becoming and all the different services that people are relying on, the applications that they're using on a regular basis. And you think back maybe 10 years ago what that home network picture would have looked like. It probably would have had, the average home would have had a plain old telephone line, a POTS line to it. It may have had an ISP service into it with one computer. And so you can, when you think about that contrast, you can imagine how complicated this is getting for consumers. And then, of course, how frustrated they get when things don't work. They just want it to work, right? So let's go to the next slide here and talk about this concept of digital harmony in the home. So our customers they're not very tolerant, right, of disruptions and slow speed. So put yourself in their shoes, right, and think about, for example, right now at this very moment, I'm telecommuting, right? So I'm presenting to all of you, and if my network doesn't work, it's pretty devastating if I have to drop off in the middle of my presentation, right? Or, for example, maybe you have all your family over for a nice, football game and nice afternoon, and you have annoying disruptions and pixelation in your service. You'll get pretty frustrated, right? So that's one of the reasons why we test, right, is to make sure that that all works. And the other reason, right, is to help our service provider customers make sure that they can deliver things profitably and effectively. So all of these different folks here in the service providers are under pressure. They're feeling the pressure of making sure that services are running correctly, that they are meeting their time for rolling out new infrastructure, that they go and have a very efficient customer call. And then finally, the operations manager, of course, is trying to manage many different types of calls a day, new rollout infrastructure, and just make sure that he's got it all under budget and on time. So with that, I'm going to turn it over to Thad, who's going to start by talking about new broadband horizons. Thad, I'll turn it over to you.
Great. Thank you, Stephanie. So we'll start with the new broadband horizons, and specifically I want to talk about FTTH and how that relates to G.fast and V35B. The G.fast and super vectoring V35B profile, they're new standards for XDSL, new standards from ITU, and these standards are really derived to extend the broadband or bandwidth availability over copper pairs, specifically very short copper pairs. So these new profiles, they really fill a gap or speed gap between VDSL2 and VDSL2 bonded services and fiber to the home. And they offer a real cost and time advantage over fiber to the home, particularly in brownfield environments. If you think of a case where I can take fiber and I have to dig a trench through a yard, I have to do aerial fiber, it makes a lot more sense to take the existing copper drop from that home to deliver that high-speed internet service. So this greatly extends the lifespan of existing copper plant over these short loops. And this can give you up to 1 gigabit per second speed. This is an aggregate speed, so this could be 800 megabits per second down, 200 megas per second up, or 500 meg up, 500 meg down, etc. Now these standards have been within the standards bodies for a couple years, but the labs and the field evaluations have been going on for the last few years. Now we expect most of the commercial deployments to be in 2017, probably middle of the year, and they're leaning really towards multi-dwelling unit deployments. And this makes a lot of sense if you think from a fiber run to a multi-dwelling unit and then using a G.fast DPU to then distribute that high-speed internet over the existing wired plant. So whether that's coax or twisted pair, it's a lot easier than trying to run fiber through an entire apartment complex. Now obviously this requires very short loops and it requires deep fiber penetration closer to the end customer to support this, as well as new equipment such as DPUs and new modems. There are several players within this market. From the chipset standpoint, Broadcom and Scipio are really dominant at this point. And as you can see on the slide, there's several hardware vendors. This is not all of them, but it's a very vast field at this point. So if you look at XDSL and fiber to the home, the topologies and how they evolved, if we look back 10 or 15 years ago, ADSL, ADSL2 Plus services, we typically had a CO, central office resident DSLAM, 10 to 15,000 feet of copper loop to deliver that high-speed internet service. Now as we went to the fiber to the node or fiber deployment, we moved those DSLAMs out into the field to these remote terminals. And typically these remote terminals were anywhere between 6,000 and 8,000 feet away from the end customer, which really allowed us to deliver fairly good VDSL services, VDSL and bonded services over that loop. And that really supported a lot of the IPTV rollouts. With the broadband wars within North America, now we've moved that fiber even closer to the end customer. So we've taken these DSLAMs and these remote terminals, we made them smaller as part of this FTTN deployment. Now they're lower port density, but they're a lot closer to the end customer, anywhere 2,000 to 3,000 feet from the end customer, which really gives us some really great services over that VDSL. And we mixed in the vectoring along with that. But what these new technologies allow, specifically V35B, is this is a new line card for that DSLAM. So we can put in a new line card of that DSLAM, expand the bandwidth that we're using up to 35 megahertz, and deliver some very good services to that end customer. Now, as we push that fiber deployment deeper into the customer, we're running fiber down the street. It makes a lot of sense to use G.fast. In this particular case, I can use the last 300 to 400 feet of copper loop to support G.fast to this fiber-fed DPU. Now, these fiber-fed DPUs can be anywhere from up to 32 port DPUs within the MDU, or they can be as small as a single port, full port, or 8-port DPU, micro DPU in the field. Incidentally, these can get deployed 200 to 300 feet from the customer, which is very close to what that average drop length for most customers in North America. And then finally, our existing fiber to the home and GPON deployment kind of goes hand in hand with this. In many cases, we're seeing G.fast is as much a fiber to the home deployment as it is an XDSL deployment. And these technicians are, Tier 1 technicians are evolving to cover all of these different technologies, whether it's fiber or XDSL and copper to the home to deliver these type of services. So with this fiber to the home, it brings in lots of problems, particularly as we stretch that fiber to the home deployment right to the end customer and the access network. The optical loss budget becomes that much more critical, and so there's a very low tolerance for mistakes. In this particular case, you can see how your optical loss budget is tuned towards expectations of 1/4 dB of loss at a connection. But if we got a dirty connection, we have 4 to 5 dB of loss, and that service is either not working or it's substandard. So these are the type of things these technicians really need to understand and be sensitive to. Okay, as Stephanie said, we're going to go over some of the high-level best practices for these different areas that these technicians will be exposed to. So the best practices for the fiber to the home testing. The first is what are the pain points for our customers, and the biggest one is really that fiber in-face condition. That's the number one. It causes lots of loss, reflectance, damaged equipment, and system failures. The second is, as I mentioned, that optical loss budget. As we've pushed the boundaries of that, it's very critical to make sure those optical power levels are sufficient for the service as well as not too high to damage equipment. And then lastly, more on the construction side, poorly installed fiber, whether it's too long, excessive bends, broken otherwise, is something to contend with, particularly as a lot of this is being contracted out at this point. But some of the types of issues that can be seen in the field are like micro bending, macro bending, whereas micro bending, where just microscopic fiber deformations within the fiber itself can be caused by external pressure, water freezings, for example, backfill of rock and everything on buried fiber. And then in the macro bending, this is just the poor installation from day one, over clamping, too tight a radius bends within the fiber that causes loss of optical power. So where today is the fiber inspected and the power verification occurs? It occurs in all these different areas today within the core, the metro, and then access in the premise and enterprise network. But the points of test are much greater in the access and premise networks. So much greater points of test means there's lots more inspection and power verification be done, but it's also a greater opportunity to introduce contamination into these points of test and connections. So if you look at the typical tests that are done from the construction side for architectures fiber to home all the way to this hybrid fiber and DSL, i.e. G.fast, the first is the fiber inspection, IBYC, inspect before you connect. So we're just going to use an inspection scope to look for contamination and test that fiber into the ISO standards. Next is the fiber characterization. We're just looking at loss on the fiber through the splices, connectors, and splitters, looking at a reflectance, and then we're going to look for those bends and breaks. And then lastly is the qualification of installed equipment. So we're going to look at our calculated optical loss budget and compare that to our actual test, and then look at the total optical return loss. Now this is more evolving here on the service activation and troubleshooting side for fiber to the home. As I mentioned, many technicians that may in the morning be doing POTS testing, copper plant, or an XDSL service may find themselves doing fiber to the home in the afternoon. So it really leads the need for having a combined solution such as the OneExport that can cover those different aspects that technicians needs. So using the OneExport and a fiber inspection scope, you do with the P5000i, you do the inspection. as well as you can do this power test and test to make sure you've got the proper power levels at the end customer that's within the optical loss budget. Next, on the troubleshooting and maintenance side, using OLP88 or an OTDR, we would do the in-service loss testing. We look for OLT identification, make sure we don't have any alien or rogue ONTs, and then we'll use our OTDR to look for in-service breaks or faults isolation in case where we're getting low power levels or no light at all. And the best way to do this is with a filtered OTDR. It uses an out-of-band wavelength 1625 or 1650. So this allows you from the premise to shoot the OTDR upstream through the splitter without taking down other in-service customers. So it allows you to not have to take apart so many connections within the field to diagnose faults within that fiber length, and it reduces the possibility of getting further contamination. And then finally, more on the maintenance side, an optical monitoring system. As I mentioned, all these different points of test within the network, and getting this contamination can ruin your optical loss budget even at one connection. But it's more beyond that service being damaged by that contamination. It's the connectors themselves can be damaged. So mating these dirty connectors, it embeds and it spreads debris into the fiber and into the network terminating equipment. 2 pounds of insertion force of a fiber over this 200 micrometer surface is equivalent to 40 to 45,000 psi. If you consider it takes 2 to 3,000 psi to crush a car, you can easily see how this debris can cause pits and chips that remain on the fiber. So even after cleaning, the fiber is contaminated and damaged and can cause back reflection, insertion loss, and other things, as well as even a complete failure of that service. Unfortunately, most of these connectors in the field, they're inspected when a problem is detected after this permanent damage has already occurred. So that's why we, as a best practice, we always preach IBYC, inspect before you connect. So this is inspection before you connect of not only the patch cord, but also the bulkhead side, because those very often are dirty and problematic. So the first step here is using the probe microscope. We want to inspect the fiber. If the fiber is dirty, we'll clean it. If it's clean, then we'll do the connection. If it's dirty, we recommend you do a dry clean first, inspect it. If it's still dirty, wet clean, and then finish with a dry cleaning, and then re-inspect and then connect. So it's a fairly simple process for technicians, and that being a part of their general methods and procedures saves a lot of time in the long run. So that's really being proactive about your inspection. There's lots of benefits to that inspection and cleaning and being proactive. It's reduced network downtime, reduced troubleshooting, so you have less truck rolls, service calls, as well as saving time for the technician. It's far easier to get into practice of inspection before you connect, rather than having to swap out OLTs, etc., because you've contaminated them and made them dirty. Optimize signal performance is another benefit, as well as prevent network damage. In the early FTTH deployments, there was an enormous number of the OLTs that get returned back to the factories. Once they're cleaned, they found that there's no trouble found with them, and or if there is trouble found, it's due to some contamination or permanent damage. Okay, so now we'll move on here to the XDSL and talk a little bit about best practices for that. One of the service provider's big pain points within this copper plant is it is in the harshest environment imaginable. It's outdoors, and so we still get reports from customers that still is 75% of the problem, from that end customer to that D-slam over that copper loop. So that's always been the case. So what's really changed here? The copper plant testing and pre-qualification, it's always been critical, but it's more critical than ever now for the XDSL deployments at these higher speeds, particularly VDSL, and now as we talk about G.fast, it's more critical. So we're using this higher spectrum, and this higher spectrum is a greater bullseye for noise issues. So more noise testing is really needed. as well as we're getting more mature deployments or existing FTTN deployment. So there's a lot more XDSL in these binders, so the noise floor is raising, and or we've got one poorly balanced pair within this binder that's creating havoc with all the services. And lastly, what's really changed here is more real-time services, and this is IPTV and real-time content. And very detrimental to these services is impulse noise issues. And so, impulse noise and noise issues is really what's changed as far as what needs to be tested with these new services. So now let's take a look at the XDSL G.fast turn-up and problem segmentation as a method and procedure. So this really relates to a micro DPU deployment for G.fast, but it can apply to other types of deployments as well. The first step here for a technician is I need to verify that that fiber is good. So I'm going to inspect it for cleanliness. I'm going to check power level. If I don't have the power level there, then obviously the MDU is not going to work. If I don't have power, then it's either diagnosed at that point by the technician with OTDR, or it's turned over to a different crew that did the construction or pre-qualification of that fiber run. But assuming that's good, the fiber gets connected to a DPU. Now I'm going to test the customer side of the DPU, and this is using your tip ring and ground and doing a G.fast sync at the jumper cable. Now if it's utilizing reverse power, you'll have to provide the reverse power to get the G.fast sync. Once that's done, and assuming it's okay, you're going to verify the copper back to the customer, and then look also at the customer side if it's applicable to see if reverse power is being provided from that customer. And then finally, from that point, check throughput. And the best way to do that, as we'll discuss, is a TCP speed test. Then third, outside the customer premise, and this really gets into a typical XDSL turn-up, but we're going to do an XDSL sync and G.fast outside the NID. We're going to verify that copper back to the DPU. We'll validate reverse power coming from inside the customer's premise, and we'll check throughput at that point as well. Now, for those who aren't familiar, reverse power is we're using the power from the CPE within the customer premise to power up that DPU. So that DPU is a fairly low port density, as I said, 1, 4, or 8 port density. And so its power requirements are quite low within a G.fast standard, so a single CPE within that customer premise can power that DPU. Now once I get into the customer premise, XDSL G.fast sync at the CPE location, that's typical. Now we're going to check the home wiring. So whether it's a wired home, we'll check that. If it's a Wi-Fi home, we'll check that. And then lastly, we'll do the final TCP speed test, throughput test from that customer to give the true customer experience. So in noise testing on the copper plant for XDSL, noise is any unwanted signal in that spectrum of the frequency used by the technology that you're deploying. It's important for technicians to know that every pair has some noise on it, unless he finds the theoretical perfectly copper plated pair. So it's very important that he understands the threshold he's testing to, the pass-fail thresholds, the frequency range of filters he's using, as well as the point of test. So noise test by itself, a result, is not very valuable until you put it in perspective with the thresholds, filters, and we're exactly within the loop that you're taking that test. Now for identifying a noise issue, once you've determined it, the first step that's most important is really to the source location. Is it inside the cable or is it outside the cable, inside or outside the home? So ingress is noise from outside the cable. So this is like household appliances in home or AM radio, ham radio outside the home. Then we have egress, which is noise inside the cable from crosstalk and other DSL services. So really the first step here is to do our narrowband, wideband noise measurement. Is that a pass or fail? And then we'll check pair balance. Is it a bad pair or is it really a strong source? I got to have a bad pair with a acceptable noise source that's detrimental to that service, or I could have a really strong noise source that's getting coupled into a reasonably good pair. And the next is your point of test. You expect to have different pass-fail criteria, whether you're testing at the remote terminal or whether you're testing outside the customer's home. And then what does the pair look like on spectral? So if I look at spectral analysis and it has a constant energy that looks like RFI or AM radio, then I know that's something that's coming from outside the cable pair. If it starts to look like a DS1 circuit or another VDSL PSD, then I know that's coming from something inside the cable. So using these steps to isolate the problem can really help technicians. The next we'll get to the impulse noise test for XDSL. As I said, impulse noise is very detrimental to these services. It's something that cannot be handled in most cases within the XDSL physical layer, and it's impulse noise protection, or the middleware level within, say, IPTV. So it's important to measure these and understand that the correct pass-fail criteria, the frequency range for the filters, and how long you measure. So this is typically, you set a pass-fail criteria, you do a test for, say, for instance, 1, 3, or 5 minutes under the filter of the technology that's being deployed, and you're just looking for counts. And however many counts you can set as your pass-fail criteria. Now, more difficult, of course, is isolating where these impulse noise sources are coming from. So it's important, once again, to segment inside or outside of premise. So you can test disconnect from the home, test impulse noise back towards the central office, or you can test into the home once the modem is disconnected to isolate from in-home or out-home. If you isolate it within the outside the home, then you can test at different locations. Right there at the mid, the cross box closer to a remote, you're looking for an area that's worse off. So you start looking for common offenders. As it says within an in-home, if you start to realize that you've narrowed it down to a certain location, it works well to use a tool such as an RF wand. This will really help you localize to a specific item that's causing an impulse noise, whether it's inside the home or in the outside plant. And then finally here with the XDSL, the physical layer testing, to do the sync, the first thing to look here is see, is my rate provisioned correctly or not? And that's going to be looking at the actual rate. And then I'll look at the max rate and what that capacity is. And that really tells me what overhead I have within that service to accept more noise on the line. And that's really looking at the noise margin. Then I'll ask, do I have any errors? Are there any CRCs, FECs, or some uncorrected G.IMP retransmissions? And it's always a good practice for these technicians to have them look at the bits per tone graph as well as the quiet line noise and H log, because these are great leading indicators to copper faults on the line. Okay, so now we're going to move on to the best practices within the home wiring. In this particular case, and this is very typical of some IPTV services, where we'll run, whether it's fiber to the home or XDSL to the residential gateway, we'll utilize the existing wire plant within that customer to distribute IPTV services. And so although these cables may have been okay for previous services, for IPTV often they're not. So they can have shorts, opens, cuts, unterminated ports and things like that that really causes poor frequency response, and they impair the video and data throughput. So being able to quickly isolate where these problems are for a technician is key to really helping move his jobs along. Having to manually trace out coax around the home looking for issues is very difficult. It's better to be able to use a test device that really maps out the network and points to the fault, so that technicians not climbing up into a 135-degree attic for no reason at all. So we really look at the best practices for this home wiring, and here's a typical example. It's XDSL to residential gateway over copper, and then we're just using coax and HPNA to distribute to IPTV. So the first step in this is doing wiring test. We're going to map the coax plant, and we're going to look with a single-ended, multi-ended test process to find out any faults. And this can be done with a ONX 580 in addition to the accessory products, the Smart ID Pluses. If I find any faults, I'm going to repair those, and then I'll connect up the CPE. Once the CPE is connected up, I can do an HPNA test, look to see if I can isolate to any problems to a network leg or even out-of-box cellular device, troubleshoot if necessary, and then retest. So now I'll move on with the best practices for Wi-Fi. Now, if it's a home where you obviously can't do the wired approach, then many are moving towards Wi-Fi as the preferred distribution of IPTV to the set-top boxes. In cases where it's obvious there's going to be a lot of troubleshooting on the wired side, it's easy to swap out to the Wi-Fi. In many cases, Wi-Fi is just used as the first choice. So Wi-Fi is very capable, meaning to distributing its content in home, but it's very vulnerable at that. And it's a variable performance medium throughout the home, which the problem with this is the customers don't have a variable expectation. They expect every device everywhere to work exactly how it should at the best speed possible. So we get a lot of this from the service providers is help. How do we fix this? And some of the metrics that we hear are outstanding. You know, for example, 30% of trouble calls are Wi-Fi related, 50,000 plus Wi-Fi calls within a month, or 50% of their Wi-Fi installs require repeat calls within 30 days. So this obviously, you know, increases the operation costs of these deployments greatly, as well as you're really lowering the customer satisfaction with these Wi-Fi services. So the first is a look at the Wi-Fi signal loss, and it's important to understand that the signal strength, it's attenuated by the square of the distance. So if you're setting the AP in the corner of your family room at the far side of the house, it may work very well within that family room. It may look a little less well within the kitchen, but then when you look at your teenager, tech-savvy, loud teenager that you put in the far remote bedroom, you might have problems there. And then passing through structures and materials within the home can further impact this attenuation as well. So things such as stone brick or masonry can cause these type of issues. Concrete or even plaster walls with the metal latticing can cause these type of issues. Mirrors have been very devastating to these Wi-Fi services. Radiators or any type of metal type devices such as shelves and filing cabinets can contribute to attenuation of the Wi-Fi signal, as well as fish tanks and those other types of fish tanks. And even large groups of people can very effectively attenuate your Wi-Fi signal. Also, when we start to look at 5 gigahertz versus 2.4 gigahertz reach, it's important to know that that 5 gigahertz reach is a lot shorter. So you may have your access point and have everything tuned to 5 gigahertz from a client perspective, but realize in certain cases you may actually get better rates at 2.4 gigahertz once you get a certain distance away from that access point. So it's really important to understand the mapping of the home and the geometry where the access point is relative to the primary spots in which you would expect to have Wi-Fi services. In many cases, this can't be alleviated by a technician as much as best effort and educating the end customer on expectations. So first here, we want to look at the best practices. How do we improve that signal strength coverage? And the symptom here is really pixelated video for IPTV, slow speeds for internet browsing. And from a test perspective, you'll see the low signal strength. So the noise level seems to be okay, but you got the low signal strength. So the actions here is really to move or reposition an access point closer to a more centralized location. We want to try to circumvent some of these typical signal path obstructions like we talked, making best effort there, as well as some cases updating the wireless equipment. So some of the older access points may not support some of the new standards for multi-input, multi-output and beamforming. So swapping out these in your chronic Wi-Fi issues can help as well. Also, installing wireless bridge or repeaters, as well as just changing band. In the previous example I showed you, you can actually get better rates in some cases by going from 5 gigahertz to 2.4 gigahertz. And as a last result, installing a wired connection. Next, we'll talk about the competing Wi-Fi network interference, and this is another problematic issue within the Wi-Fi deployments. The first tier is co-channel. So co-channel is when we have multiple APs that they share the same channel. When they share the same channel, then the collision avoidance protocol, it manages how these access points access this channel. The next is the adjacent channel. When you have APs that occupy channels adjacent to each other, you get this overlapping of spectral profile. So this overlapping is just seen as noise, and this noise lowers your SNR of your primary channel that you have your service on. And then finally, the non-Wi-Fi interferes. So these are non-802.11 RF emitters that overlap within the Wi-Fi bands, and they can contribute greatly to the detriment of the service. Increasing distance between the non-Wi-Fi interferers and Wi-Fi equipment is really the solution in that case. So next, look at how to reduce noise, and the symptom here is very similar. Pixelating video, can't connect. Once you do your testing, you'll see, hey, my signal level is okay, which, you know, this is a fallacy in many of the early deployments in which technicians would look at their set-top box and say, hey, I got 4 or 5 bars, I'm good, which is not necessarily the case. You could have noise or utilization issues within that channel. So looking at the actions here, we're going to limit our higher strength adjacency. So we want to lower the noise level from those adjacent channels. We want to try to detect and locate and mitigate these non-Wi-Fi interferers as well. And we can do that with a Wi-Fi spectrum analyzer to, one, see if they exist and try to narrow down where they are. For example, you could have the microwave oven that's old at one particular customer. You can't necessarily swap out that microwave oven, but does it really make sense to have that access point right there in the kitchen, which is frequently the case. And the last step here, if all else fails, of course, is to go to a wired network for whatever access point is or end client is having the difficulties. The next we'll talk about channel utilization, and it's really important to understand that Wi-Fi is half-duplex. So all of the devices of the APs, they're on a single channel. They share airtime. So if one of them is talking, they're all listening, and this is part of the collision avoidance algorithm. So only one can talk at a time. So we get this channel utilization, and this is measured as a percentage of time that the Wi-Fi network's channel is occupied with energy such that another API client cannot transmit. So if I got 100% utilization, that means no other client or AP can transmit within that channel. And there's really two parts of this channel utilization. You could have utilization due to Wi-Fi activity in the channel, or you could have it due to non-Wi-Fi activity in the channel. So to give an example of this, we could take 2 apartments, Bob's apartment and Tom's apartment. And if Bob's apartment is transmitting from his access point to a client on the same channel, then Tom's apartment, his client and access point are all on standby using this collision avoidance, and they will not transmit. Same is true when I look at Tom's apartment. When Tom's client is transmitting to his access point, everything within Bob's apartment is on standpoint. So it may not even be your network, but it could be your neighbor's network that's utilizing your channel. This gets really important in MDU environments. We have multiple apartments, and they're many times on the same channels within Wi-Fi. Next concept here within this testing and best practices is the fire rate and how that varies versus SNR. So if I'm very close to an RG, most packets are sent at the highest fire rate. Now, as I get further away from this RG, the SNR gets a lot lower. As this SNR gets a lot lower, the fire rates change. So I'm going to be using much lower fire rates as I get further from that access point. So this can cause a lot of problems in some of your far-reaching areas of the home, in which case realize this is all on the same channel. So closer clients at access point will transmit at a high fire rate versus the further ones out will transmit at a much lower fire rate. And so what the effect of this is the low fire rate requires more time to transmit that same amount of data as the faster fire rates. So effectively, if I've got one client that's very far from my access point, it will utilize a very low fire rate, and that low fire rate will take a long time, which means it's it's overutilizing that channel and preventing other access points and other clients from exchanging data. This is also the case of older Wi-Fi equipment. So I could have, for example, a neighbor, remember the Bob and Tom's apartment. One could have an older 802.11a access point and a device, but it's on the same channel. And because it's an older device, it's going to use a lower PHY rate, so it's going to take its unfair share of that channel as far as utilization, and it's going to impact the other apartment that may have a newer, higher speed service. So how do we optimize this utilization? The first thing here is we want to move to a channel with lower co-channel occupancy, and we try to make use of the higher 802.11 PHY rate. So in this case, you're moving access points and in clients so that you don't have any of those low PHY rates. Move to even a different band. In many cases, if you're using 2.4, 5 gigahertz is generally less crowded in most areas now. And then also you can change your channel width. So I can increase the channel width if the adjacent channels are clean, or if I got a broad channel width and adjacent channels are noisy, then I can decrease that channel width. Okay, so now we'll take a look at speed testing and how that fits into the end customer's quality of experience and some best practices there. So the speed testing has been a service provider pain point for many years, and it's really the case of a customer paying for a service, even if it was a 10 meg downstream XDSL service, or even it's a 1 gig service now. It's very easy for that customer, an educated customer, to use free applications like Ookla to do their own self-speed test and do their own testing. And very often these inaccurately or falsely present slow results relative to the provisioning that the service provider has, because it could be impacted by the customer's PC, the customer's network, or even the internet beyond the service provider in which that Ookla speed test was done. For that reason, our handheld equipment, we, as a best practice, we talk about a new RFC 6349 TrueSpeed technology, and it's really a standards-based solution to calculate and characterize the service provider's network and how it impacts that customer's quality of experience. And this is from the TCP level. Now, this standard really evolved as part of Metro Core testing, but what we've done is we've extrapolated that towards a more simplified approach for how Tier 1 technicians can test at the residential. So what is this RFC 6349 TCP through test? First is it's an ability we can do a valid quality experience for that customer. So we're not going to do an Ethernet test. We're not going to do a DSL sync. We're going to look at the quality experience and test it at the level that the customer utilizes it, and that's at the TCP applications level. So whether that's web browsing, Google, Facebook, or business apps, or streaming video from Netflix and YouTube, or even our mobile apps, we want to test it from that customer's point of view, but we want to test it within known controllable constraints within that service provider's network. So the first thing we'll do with this RFC 6349 is we're going to do a bidirectional TCP throughput test. So we're going to do an upstream and downstream TCP throughput test, and we're going to calculate what the optimum window size is for that bandwidth that's provisioned. And by calculating the optimum window size, we can have a near 100% TCP efficiency, assuming nothing's wrong with the network. If we see TCP efficiency is less than 100%, then we know that the network is impacting the TCP throughput. So this allows us to provide some pass-fail results versus actual versus what's expected. Because by knowing the ideal window size and the number of TCP sockets to open, we can calculate what that bandwidth should be, independent of the window size, the PC impacts, and things of that nature. And secondly, the TrueSpeed server, it retains all that TCP analytics for the speed problem resolution. So even though the end clients may show a simplified version. At each test, the server retains all that TCP analytics for some very in-depth troubleshooting capabilities. And this RC6349 TrueSpeed, it's available as a virtualized client as well as a client application for our handheld test equipment, like the OneExport, for example. So if I start to look at bursty versus constant traffic applications, obviously UDP is just that, it's constant. But when we look at TCP, it's bursty by nature. That's the way the RFC is. And whether I'm doing HTTP, I'm doing email, I'm doing download on YouTube or Facebook, at times this TCP burstiness can burst above what my line capacity is. And what that looks like is TCP retransmissions. And so on particular lines, particularly if you've got network elements that are misprovisioned, such as policers or routers, you can have a lot more TCP retransmissions. And so the customer gauges their quality experience on what we call good put, not necessarily throughput. So the good put is what gets to the customer without being retransmitted, versus the overall throughput would include all the retransmissions as well. So if we look at a use case here for a particular case of an ONX 580 as a residential customer testing all the way to our TrueSpeed VNF server on the provider edge router, this is a very simple test for a technician to segment and isolate multiple points in the network. So you can run this test at the Ethernet interface up to 1 gig over from the residential gateway, from the customer's PC, as well as go outside the home and disconnect the NID and do a speed test or a tip ring and ground. As further, you can take that to the crossbox or even a remote terminal to do this TCP level throughput test. So it really helps that technician to isolate the speed problem within that service. So is it a misprovisioning problem, or is there a network element that's causing a problem, or is there something within the customer premise or within the access plant that's causing that problem? And that's pretty powerful for a technician to solve these type of speed issues, particularly if he can turn over the problem and say, hey, it's definitely not within the access network, it's in the core network that's causing this TCP inefficiency. With that test result that he's run is all resident within the VNF server. So that can be pulled out, all the detailed TCP analysis can be pulled out by a Tier 2, Tier 3 engineer to diagnose what may be in the network causing that problem, whether it's a router, policer, or buffer that's causing those type of issues. That really allows a deep dive on it. And it allows the technician to really replicate these issues from the end customer's point of view in a quick and simple 1 minute or less test. Okay, in the summary here, as I mentioned through this, it's the technicians today, the Tier 1 techs, they have broad responsibilities. They're not just POTS techs, they're not just in-home techs. Many times they have responsibility for DSL, GPON, and the future G.fast. They have to go inside the home, deal with POTS issues and Wi-Fi and coax cabling and Cat3, Cat5, Cat6 issues. A broad different types of physical plant problems that they may have to diagnose on any given day. And then at the customer level, looking at the IP services, whether it's voice, video, data, or even the quality experience using the TCP throughput with the TrueSpeed. All of this is very much needed by a single tech today. So with this, ONX 580, it meets all these needs, but there's also accessory products that help it as well, depending upon the responsibility of these technicians. So if it's someone that generally just has copper responsibility, there's a far end device. There's the RF1 for noise, impulse noise testing. If this technician has responsibility for in-home, there's accessory products that do the coax mapping and diagnostic with the Smart ID, as well as the 2.4 and 5 gigahertz in-depth Wi-Fi testing with the Wi-Fi advisor. Now, if it's a technician that has this fiber responsibilities as well, there's the optical power meter accessory that goes with the OneExport, as well as the fiber inspection scope. And then lastly, our Smart OTDR for those cases where there really is a need for some more in-depth troubleshooting on the fiber side. That's in the presentation. At this point, I'll turn the presentation over.
Thank you, Thad. That was an excellent presentation. At this time, we would like to address some questions that have been submitted. As a reminder, you can submit a question using the Q&A box at the bottom of your screen. If we don't get to your question, a Graybar representative will follow up with you after the presentation. We've got a couple of that have come in here. Okay, the first one. What is a good pass-fail for utilization on Wi-Fi channel?
Sure, that is a good question there. It can depend upon the customer and the service provider and their history and use cases and what they've seen. But a general starting point is you want to see utilization less than 30 or 35% of that channel, and that's in a low noise environment.
All right, thank you. We have one more here, it looks like. Does non-802.11 interference show up as noise in the channel or high utilization?
Yes, that is a good question. It can actually show up as both. So if I have a non-802.11 interfere within my channel, if it's strong enough, say in the neg 50, 52 dBm, then the other access point will see that it will utilize its collision avoidance and not transmit. So if you've got a non-802.11 interfere that strong, it will look like 100% utilization of the channel. Now, if I got a lower level from a non-802.11 interference, let's say it's like neg 75 dBm, then that will just look like noise on the channel. So it's going to lower the overall SNR on my channel. And when it lowers that SNR on the channel, it's going to cause my access point to use lower PHY rates. And when it uses lower PHY rates, then that's going to effectively change my utilization of that channel. So really a little bit of both.
Thank you, Thad. As a reminder, again, as I said, you can submit any additional questions that you have at the bottom of your screen there through the Q&A box. I don't see any other ones coming through right now. Give it maybe one more moment. Nope, nothing right now. So, well, we are about out of time at this point. If we didn't get to your question, a Graybar representative will follow up with you after the presentation. As a reminder, this presentation will be archived on the graybar.com website. Again, thank you for your time today, and we hope you will join us again next month for Graybar's G2 Talk. Thank you, everyone.